Finding the inverse of a 2 by 2 matrix. Here's a matrix A. Find the inverse of A if it exists. Once again, this isn't the greatest mathematical grammar. It should say if the inverse of A exists, state what it is. State the inverse of A. I guess I could change that to an if-then statement. If I'm talking about very, very proper mathematics, then state the inverse of A. We're going to go ahead and find the inverse of A. I'm actually going to use a technique called the Gauss-Jordan technique. Or sometimes it's called the Gauss-Jordan elimination. Gauss-Jordan technique. And what this does, it is a trial and check method where we're looking for a very, very specific row reduction. The Gauss-Jordan technique goes something like this. You take your A, you take your square matrix A, augment it with the identity, with an n by n identity, then you perform a bunch of elementary row operations. And if you get an identity on the left and augmented with a matrix B over here, then the conclusion is that B is in fact the inverse of A. And that's what we're going to do. We'll take the matrix A, augment it with an identity. So your first matrix is going to be size. What's the size? Think about it. Augment it with the identity. So your first matrix is actually of the size 2 by 4. Let me draw that line dotted because I think that's what your textbook uses or your software uses. And now we're going to row reduce. And we're going to row reduce in such a way where we want this as the outcome. We want the identity on the left-hand side, and then whatever you do with the row reduction, hopefully it yields a matrix on the right-hand side of that augmented line. I guess to be consistent, that should be dotted. Let's make that a dotted line. Dot, 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 dotted line. It's the same dotted line over here. Okay, let's get that leading 1. First thing I notice is I could do row 2 added to row 1. And if I draw that arrow, that means row 1 changes. Row 1 gets the new storage. Now row 2 doesn't change, so I'm just going to copy it over again. And we're going to change row 1 now. We get a 1. And we get a 1. Row 2 plus row 1 and a 1. Oh, that's convenient. Now we would like to get a 0 right here using elementary row operations. We're going to go ahead and scalar multiply row 1 and add it to row 2. What are we going to scale multiply by? We're going to go 3 times row 1 added to row 2. And if I draw that arrow from left to right, that means I'm going to store in row 2. If I store in row 2, that means row 1 doesn't change. So I just copy it over. Now we get a 0 here. And we get 3 times row 1. So 3 plus a -4. -1. 3. And then a 4. Nice. Now we get negative row 2. We could scalar multiply a single row. And I'm going to store in row 2. Remember that tilde means row equivalent. Row 1 doesn't change. I'm going to recopy that. And we get 0 now. 1, -3, -4. We would like this position to be a 0 using an elementary row operation. So now I'm going to do negative row 2 added to row 1. And we get 0, 1 for row 2. Row 2 doesn't change, so -3, -4. And we get a 1, we get a 0 here. Now we got 3 plus 1 is 4, and 4 plus 1 is 5. Aha! Notice, on the left-hand side of this dotted line is the identity matrix. What does that mean? That means we actually did find the inverse of A. The inverse of A is over here. So let's make our conclusion. Therefore, the inverse of A is indeed going to be 4, 5, -3, -4. And one way to check, I'm going to leave this up to you. If you don't believe that's the inverse, you could check this. I'm going to let you check it. You check what A times the inverse of A is, and as a separate check, you're going to do the inverse of A times A. So if you multiply these two sets of matrices, you should get something very, very interesting.